In the previous episode, we theatrically discussed the circumstances needed for life to emerge and the larger-scale criteria for the long-term stability of life. Today we'll cover the emergence of macrobiological ecosystems and the diversification that follows. We closed the last episode with the introduction of Lapis's two main lineages of multicellular life. Two exoflagellate colonies that we'll refer to as Xanthofolifera and Exotheria, respectively. Xanthofols possess yellow pigmented chloroplasts that let them create energy from the golden sun itself. Exotheres, conversely, are obligate heterotrophs. They must consume other organisms to survive. Large organisms have yet to emerge on Lapis. If you were to step out onto its pristine beaches, there would be no signs of multicellular life visible to the naked eye. Lapis looks more or less the same as it has for the last billion years, since the exoforms evolved. Life has remained very stable, and arguably stagnant in that time, let alone the billions of years Lapis spent stuck in a chemosynthetic cycle of worldwide anaerobic debauchery. If you've ever seen the grimy chromatic mosaic that is Yellowstone's Lower Geyser Basin, you've got a solid grasp of Lapis's visible life. Microbial mats cover nearly every underwater surface on the planet, structures so densely filled with life that gases trapped beneath their matrix force up lumps, hills, and spires onto the alien aquascape. As ages pass before these sprawling masses, they literally harden to stone. Although these biomes only exist in grandeur in Earth's most extreme conditions nowadays, Earth spent 4 of its 4.5 billion years as a world of microbial mats. If we find another world that harbors life, statistically, it will be a world like this. Quite literally, a primordial sludge. Perhaps life in its truest form, microbial mats are worlds in of themselves. Constructed from trillions upon trillions of organisms, many capable of their own movement, these living monoliths are a monument to the miracle of life. Those blessed by the golden star's light are oxygenic phototrophs, the skin encasing the matrix. Underneath the sun-kissed crust is a layer of aerobic heterotrophs, and beneath them, anoxygenic photosynthesis, in which oxygen is not a byproduct, takes place. Deep inside, chemosynthetic microbes eat away at the very rock they stand on. This dense mass of life houses many different metabolisms whose byproducts directly fuel other metabolisms. A beautiful cyclic cacophony of shifting activity, a vast resource, ripe for harvest. It may seem reasonable to conclude that exotheres will simply evolve to prey upon the Xanthofols, as plants on Earth are typically thought of as the base of the food web. But Lapis is a very different place from modern Earth, at least for now. Taking on another cellular colony isn't worth the effort, especially when you're rolling in infinite scum. Both lineages can use their flagella to form currents that draw nourishment and smaller organisms into cytostomes, mouth-like structures, on their cells. The colony can distribute nutrients through their shared water pocket. These basal Xanthofols and exotheres are so simple and numerous that they may never go entirely extinct, similar to how Earth's placozoa continue on to this day. Uncoordinated tumbling works out surprisingly well in this environment. Both of our multicellular lines contain symbiotic mitochondrion equivalents, captured but not eaten bacteria that now reside and divide within each cell. In exchange for protection from the outside world, they reward their hosts with greatly increased energy potential. Xanthofols also have something extra: chloroplasts. These descendants of free bacteria contain chlorophylls, keratines, and keratinoids, specifically xanthophyll. Like plants, they can create energy from sunlight. Unlike plants, however, they are primarily yellow, with differing proportions of pigments allowing for lime and brown forms. This may seem otherworldly, but photoautotrophs can use many different accessory pigments to augment what parts of the light spectrum they absorb, and therefore the color they appear. Xanthofols bear strong resemblance to Earth's yellow algae. Tangent aside, the xanthophyliferan ability to eat starlight means that they can move away from heterotrophy and specialize for autotrophy, foregoing competition with the Exotheria. One of the most fundamental competitive edges for photoautotrophs is height. Xanthofols, as multicellular organisms, are highly advantageous due to their size compared to the denizens of the microbial mat. If you're the biggest, no one else can block your light. One line of Xanthofols may swell so great in size that they lose their mobility. Bubble Xanthofols are too large to be supported by a single layer of cells. Retaining their ancestral water cavity, they may develop specialized layers of cells to form a solid skin. These bubbles will dot the microbial mats, clustering around rocky footholds and drifting helplessly when dislodged. However, they inherit a significant flaw from their ancestors. They can only reproduce by tearing open and releasing daughter colonies. This isn't the worst shortcoming imaginable, but when hitting a pebble too hard can rupture your body before you're ready to clone yourself, it can harshly limit your habitat range. Bubble Xanthofols in choppy or rocky waters would benefit much more from clustering than their calm water cousins. Instead of hoping to cluster with other individuals by chance, they could increase their likelihood of genetic success by shielding themselves with clones. By dividing their inner cavities, they could split into two bodies before having to tear open, releasing daughter colonies upon maturity. By sticking together and forming long chains, they can decrease the chances that any one body will be dislodged and destroyed. Bubble chains under extreme enough torrent may break into stray pieces, with any popped clones helping to protect rafting survivors from damage. Once a new hold is secured, the survivors can fission again until their daughter colonies are ready to release. Being able to repopulate through fragmentation is very useful for organisms that can't reproduce sexually. This ability can be repurposed to specialize in propagation. Instead of growing in a chain, these macaronophytes can grow from a fused holdfast, buried within the substrate or clung to a rock. With more specialized tissue layers, macaronophytes can grow much larger than their simpler cousins. The clustering bladders rising from the holdfast could be called fruiting bodies. Once mature, they abscise themselves and are carried off by water currents to new territories. If a new grip is secured, it will start a new holdfast. If the bladder is sufficiently damaged, it will rupture, releasing spores. Macaronophyte spores are similar to their ancestral daughter colonies, but reduced to a single, highly durable cell. When subjected to favorable conditions, it will slowly grow into a new holdfast. This focus on reproduction will make macaronophytes some of the first complex organisms to colonize newly fertile waters. Macaronophytes are not the end-all be-all of bubble xanthofols. In an aqueous environment, size is nowhere near as valuable as simply being above your light-eating competitors. Bubble chains could adapt to favor a free-floating lifestyle rather than a clinging one, but to do so, they need to be structurally prepared for turbulent conditions. While bubble chains suffer mortal damage from colliding with Lapis's prolific glacial erratic rocks, bubble nets are significantly better protected. By incorporating spicules of silicon dioxide into their dermides, they suffer minimal damage. Like many sponges, diatoms, and radiolarians of Earth, their shells are siliceous, made from sand. These tests provide strong protection, but disallow the freedom of growth that softer xanthofols enjoy. By shaping their siliceous tests into tubes, they're able to grow sister bodies from terminal buds, forming a strong, flexible lattice. Unable to release sister colonies, bubble nets suffice with reproduction through fragmentation. Though individually very small, their lattice growth can ubiquitously plot surface waters. Of course, the exotheres have been evolving too. Similar to the bubble Xanthofols, some exotheres may grow past the point where simple flagellate movement is possible, relying instead on the motion of waves and tides. Though their budded offspring are small enough to swim, large forms become sessile, at the whim of the seas. Tumbling through an endless banquet lightens the interpretation of these apathetic organisms. Lacking symmetry and coordinated behavior, these tumble ribbons are perhaps even less advanced than the Xanthofols. However, they aren't without adaptations. Their intestine-like appearance increases their surface area. More surface area means more flagella, and more flagella means more material enters the superorganism's cytostomes. Truly, a creature harkening back to simpler times. Further evolution of tumble ribbons may be inhibited by their hapless adult forms. Instead, their able-bodied larvae may drive their future. Instead of aimlessly swimming, their larvae may put their cilia to work. By organizing into a whorled pattern, the free-floating larvae could act as stentors and rotifers of Earth, sustaining and filtering through a powerful vortex. No single cell can escape their whirlpools, and with the microscopic world at their whim, they are able to grow large. Large enough to grow sessile, permanently clinging to the substrate, they're certainly a cut above their formless relatives. We'll call them turbogellates, Whorl jellies. A significant advancement of note in this clade is the evolution of an oral pouch at the epicenter of the whorl. This pocket houses the organism's most abundant collection of cytosomes. Characteristically lacking the internal water cavity of most other exotheres, these gelatinous organisms are solid through and through. Specialized tissue layers help to transport nutrients around the body, even those far from the oral pouch. Turbogellates may be very advanced exotheres at the moment, but their newfound solidity may have run them into an evolutionary wall. Early exotheres are, by nature, very small. The early diversification of these organisms is muddied and nearly untraceable. Before sexual reproduction, evolution is wholly driven by random copy errors. New lineages can arise somewhat spontaneously with radically different body structures from untraceable points of divergence. If far-off intelligence is fortunate enough to uncover the splotched, silhouetted remains of these primordial organisms as fossils, their origins and relations will be hotly disputed for generations, and, possibly, will never be understood. Lost to time, with no conscious minds to admire them, as their fossils erode or sink into the mantle, a time will come when these early days of Lapis are gone forever. Hopefully they'll be found before then. We are but omnipotent spectators to the summation of this world's history. At some point, an exothere developed the ability to create and fuse haploid cells, the origin of sexual reproduction, a potent tool for evolution. At the verge of opportunity, Panlaminam arose. This organism has a highly defined polarity, or body axis, the precursor to symmetry. This adaptation is vastly more effective at structuring a body than the haphazard structural forms of the tumble ribbons and the mostly amorphous turbogellates. Morphogens influence cell growth and form based on proximity. Multiple morphogen sources can allow for very complex yet organized structures and developments, unlike turbogellates, which have locked themselves into a single axis of polarity due to their specialized feeding. Panlaminam too has an oral and aboral direction, but its adaptability that conquers the world, and Lapis is yet to harbor a victor. Panlaminam is a blank slate of an organism. It can become anything. A flattened disc. The oral face houses most of the flagella. As a larva, this face propels the body through water. As an adult, this is the side that contacts the substrate, whipping away at the microbial mat, mowing the surface as it wanders. Thoughtless, unwary, and with an arbitrary sense of direction, Panlaminam leave the first irrefutable evidence of complex life: trackways. In an age where motile organisms lack direction and refined coordination, these trails often overlap to little notice. When gliding over a pasture that's already been grazed, an organism may lose a significant amount of energy without taking in much food. The simplest response is to speed up when food is poor, and slow down when food is rich. But, without a defined direction, random movement can ensnare an organism with its own lack of awareness. Aimless directions can cause a deadly overlap in position, and a surefire death in unfavorable conditions. The clade Motilomorpha, sired by Panlaminam, is characterized by motility, sexual reproduction, and the presence of muscle and nerve cells. These cells, in tandem, can rapidly retract sectors of the body when presented with mortal dangers such as sharp rocks. This is very advanced for the time, but still a band-aid solution. In order to better prevent accidental suicide, Motilomorphs need to pick their directions. Radial symmetry is an easy way to segment the body. With 8 different sectors, Octoradiotherians are free to choose between 8 different directions. Like Earth's pentaradial echinoderms, individuals often prefer one sector to lead over the others. This aids in assuring that the organism doesn't double back over its own trail, while also being able to travel in the opposite direction of danger without reorienting the body. Each sector is marked with a feeding furrow, a cleft where food particles are sensed and passed closer to the oral surface. This body plan is very beneficial for slow crawling organisms, where each sector can sense the proximity of food and prioritize their direction. No wasting time or energy rotating around in search of untouched microbial mat. Sensing the trail of another organism will send them in the opposite direction. Motilomorph larvae use their oral surface as their means of locomotion. Past a certain size, they must descend to the seafloor and continue life there. However, if their aboral side is heavier than their oral side, they'll reach the bottom upside down. Luckily, these organisms are simple enough that this inconvenience merely changes their feeding strategy. The waves and currents stir up plenty of microscopic organisms into the water column. A slight tweak to the ancestral Motilomorph body could give them a muscular hood around the oral surface. This hood could contract and open around a sphincter to aid in water flow over the feeding surface. These Quadaradiotherians, or perhaps more informally jelly cups, rely on their ability to filter water, as they can't crawl to greener, or perhaps browner pastures. Their excessive use of muscular exertion means that they must rest frequently, but they are still the most furiously active of Lapis's large creatures. The fastest of Lapis's early creatures are the Dilatarians. Similar to Earth's bilaterians, having 2 symmetrical halves prioritizes a singular forward direction, as was crucial to our ancestors' overwhelming success. However, Dilatarian origins are humbler than one might speculate. Their bilateral symmetry was not immediately perfected. With a heavily lopsided growth pattern, these spiral-shaped creatures grow outward and downward from their centers, similar to snail shells. The spiral isn't for defense, their flesh is paper-thin, like most other Lapis lifeforms. This offset growth pattern provides them with the illusion of behavior. Their forward direction isn't straight, it's a circle. Randomly speeding up and slowing down gives them tighter and wider feeding arcs respectively. In an age where most competitors are extremely slow, having a circular movement pattern can help you seal off territory for yourself, even if you don't realize you're doing it. Life has swelled across this world for eons, and even the most deserted voids of open water are filled with sprinkling particles drifting out from more verdant shallows. Before now, only planktonic life, including the larvae of many Motilomorphs, took advantage of this glittering detritus rain. Large, inactive organisms rely on the microbial mats close to the surface to gather enough energy to sustain themselves. Their bodies are denser than water to prevent them from ballooning up to the surface, but this also means that large life cannot exist without the safety net of the seafloor. That is, until now. The Octoradiotherians have been evolving. One particularly successful lineage will be known, lovingly, as the sea nuts. Their frail bodies are almost entirely composed of water, giving them the gift of neutral buoyancy. They retain muscle fibers and a nerve net able to bend and twist just like more basal Octoradiotherians, but claw through the open ocean with cilia fused together into thousands of tiny paddles. They are, by far, the most mobile of Lapis's fauna. No longer bound to the sea floor, sea nuts are free to explore niches yet to be explored by large complex life. Microscopic structures along the oral surface pass specks of food down to a hole in the body cavity, where most of the organism's cytostomes reside. Sea nuts dominate this world, with species differentiating territory through depth, temperature, and particle feeding size. Be it below the choppiest sea ice or the most crushing abyss, sea nuts exist wherever the unwitting currents drag discarded scraps of detritus. This simple, orange-shaped vacuum cleaner will be a design seen on this world until its bitter end. For now, at least, they all look more or less the same. While the water column is dominated by sea nuts and the larvae of other motilomorphs, the seafloor has remained somewhat sub-optimized, with small, lethargic creatures slowly snaking over infinite fields of scum. There's significant room for improvement. Most seafloor organisms are asymmetrical or radially symmetrical, prioritizing ease of redirection over speed. A slight alteration to the growth pattern of dilaterians has led to a glide reflection known as an isomer-based structure. This organism isn't segmented. Its center line zigzags between alternating lobes, a growth pattern most often associated with plants here on Earth. Although not truly bilaterally symmetrical, this body organization prioritizes a single forward direction. The body starts with a single mass that could be considered a head, a particularly large lobe which produces more isomers behind it. The organism as a whole grows, while also producing more isomers behind it. Muscles and nerves extend under the assumed head, and outward from the zigzagging center to form a rudimentary snail-like foot. Gliding movements of its muscles and ample production of slime not only help its underside feed on the microbial mat, but propel it forward at unheard-of speeds, almost noticeable to the human eye. Aside from the thin foot, the rest of the body is composed of connected bladders to help share nutrients with the body. This isomer-constructed organism can reproduce by shedding gametes into the water, but it can also sever part of its rear to form a new organism, intact with some of its parents' memories. Less voluntarily, if torn apart by a storm, these creatures' simple alternating structure makes them easy to reconstruct from scraps. Organisms this simple find it easy to repurpose entire bodily structures. Slightly tweaking the growth of isomer blocks can cause them to grow as fractals. Each lobe is itself made of alternating lobes, and so on. Although these fractaling isomer organisms used their undersides as their feeding surfaces, such an immense increase in surface area is exceptional for passively grabbing nutrients from the water. Maintaining a muscular foot and reactive nerves is wasteful if not in use, so the fractals lost them quite quickly, reverting to an immobile adult state to conserve energy. Now, after losing all sense of touch and movement, they're easily sustained by sieving the underwater breeze. What used to resemble a head has become little more than a weighted bulb used to root the organism in the substrate. It does, however, have connected tunnels within its flesh that pass water and food particles throughout the organism. This allows their soft bodies to become fairly robust and very large in some cases. Their still rather niche resistance to turbulence will make this group very successful in shallow waters, even lodging between pieces of gravel in clear, seemingly unproductive waters. But they'll remain far from absent on every sea floor across the planet. Forming a body out of a fractal is a wonderfully simple solution to a complex problem. Reproduction can be left to shedding pieces of yourself. Every piece is just a smaller version of a larger piece, after all. Growth is only a matter of following one instruction. The bottom is a weight, and all other tissues follow the same structure. Different species of fractaling isomers are easily distinguished by their proportions and levels of complexity. Feather-like forms, chain-like forms, even forms like this, which repeat not only the lobes, but multiple fused instances of the entire body as well. This duplication makes for a bit of a cheeky shortcut to increase the species' size. Some, like this, are well over 5 feet tall, their rubbery skins holding the plant-like structure together, while the smaller pieces are free to shed into the current. You may notice that this organism isn't translucent. It isn't actually pigmented, but rather its flesh is so saturated with the yellows, browns, and purples of its single-celled food that it's practically been dyed by them. These titans of Lapis artfully dot continental waters, with similar species across the world, across all depths. Hundreds of smaller species quilt the shallower, most biologically productive zones, while very few larger species inhabit the lonely depths, seizing every piece of dust meandering by. Of course, this isn't the only isomer-based lineage to proliferate in Lapis's Eden. The muscular foot of this lineage allows them to cover ground much quicker than their now distant radial cousins, and their single direction of movement allows for their front portion to be specialized for picking up scents. Small, winding furrows under the foot pass into a central cleft, which pockets and branches inward, moving nutrients throughout the organism as a kind of basic digestive system. This structure not only allows the group to grow significantly larger than before, as deeper areas of the body can be reliably nourished, but, when combined with their speed, allows them to quickly envelop an unharvested area of microbial mat, hoarding it until it's been used up. Such complex behavior will reward their evolution kindly. In a world yet to evolve predation among organisms of similar size, defenseless creatures like this can grow almost comedically large. If you could walk across Lapis's pristine white beaches down to the slimy shallows where this giant slogs along, a simple poke could tear right through it, despite being almost 4 feet long. This beast is adapted for waters only a few inches deep at low tide, with miles of flat, yellow-brown pasture to glean. In order to exploit such aggressively sunlit waters, these isomers have developed another milestone: UV protection in the form of melanin. Even very large species can safely withstand the golden star's intense radiation. While these advancements have made this group remarkably successful, specialized giants, like this species in particular, are often the first to go when environments change. Life on Lapis is growing big enough to have a profound impact on the ecosystems it finds itself in. The Xanthofols have been diversifying as well. Lapis's long history of shelled microorganisms has resulted in incredible beaches, but has also left its oceans frothing with calcium. A group of macaronophytes has adapted away from rafting bladders, becoming a calcium sink, henceforth known as the stone Xanthofols. The sprawling holdfast of older macaronophytes has become the main body of the Xanthophol, with the outermost layer taking in and passing down dissolved calcium to form a base of calcium carbonate. Stone Xanthofols hold a similar niche to the stone corals of Earth, but without the extra steps the heterotrophic cnidarians bring with them. Just a photosynthetic skin around a slowly growing stone. Their bodies aren't particularly organized, with branches of new growth erupting from random points on the surface. As no xanthofols possess roots, the stone varieties are particularly susceptible to being dislodged and flipped by waves and tides. They, very slowly, reach toward the light, with skins often abandoning lower sections of their stony skeletons in prolonged absence of light, assuming they've been buried. Stone xanthofols, given enough time, effectively replace the substrate as interlocking skeletons build over the remains of others. This not only creates densely suffocating labyrinths at the edges of xanthophol reefs, but they can outcompete the bacterial mats at their preferred depths. Reefs are often thought of as havens for life, but their tough skins and sharp, often jagged skeletons pose a mortal threat to most complex life on the planet. That being said, bubble chains can't be bothered to know the difference between a rock and a reef, and do just fine. While most organisms avoid stone xanthofol reefs, their influence can be felt far from their domains, especially after storms. While some stone xanthofols can be over a foot wide, most species are less than a centimeter, and easily snap like pine needles during storms. Branches washed into deeper waters soon die, as, unlike microbial mats, they require a significant amount of sunshine to penetrate their surface. However, those blown toward the shore gather like tumbleweeds, piling up amongst the scum and sludge. They can't proliferate as wildly in waters too cold or too shallow, so they can't overtake the microbial mats in these areas, but they do act as wave breakers. They dominate life in their reefs, but here, their bones shelter more regular denizens of Lapis, allowing smaller exotherians safe access to pastures previously uninhabitable due to their body-ripping waves. This isn't a hazardless inhabitation, however. The stone xanthofols are dangers in of themselves. Navigating this environment requires durability and complex pathing, traits that mid-sized gutted isomers are capable of. Although many of the giants have had their territories fragmented by shorebound stone xanthofols, the group as a whole is highly adaptable and quick to fill new niches. Their inverted gut folds allow them to grow larger than many of their motilomorph contemporaries. In this group, the tough, muscular foot may extend upward and wrap over the thin-skinned isomers. Although still easily damaged, this extra layer of protection is vital to prevent fatality among the stone xanthofols. At their front, a wide flange extends forward and outward, a muscular tongue-like projection used to probe and smell the environment before frailer parts of the body are dragged over it. This, in tandem with their long, serpentine bodies, allows them unrivaled access to the microbial mat between tangles of xanthophol skeletons, even in the shallowest waters. The tongued isomers are the new kings of the shallows. Like their ancestors before them, they can sire new life by severing the tips of their tails, and also by shedding gametes. Meanwhile, the Quadaradiotherians, also known as jelly cups, have been adapting to exploit stone xanthofol reefs. A muscular holdfast lets them form a suction seal onto whatever they're attached to. Although this evolved to grip rocks, many jelly cups now find themselves reaching sessility on the outermost branches and bones of xanthofol reefs. The edges of the reefs block the flow of shed particles from the shallows, diverting them out to deeper waters. Before it reaches the open ocean, many varieties of jellycups have risen to take part in this resource. A weak toxin is excreted in the slime of their holdfasts, which evolved to remove scum from rock when rooting, but has come to dissolve the skin of stone xanthofols to reach and grip the shell below. If dislodged, they have a chance to reattach before drifting out to the deep, much to the scarred dismay of the reef. These more advanced forms, we'll call jelly lungs, don't only rhythmically cycle water, but can inhale an impressive volume before closing their four-lobed sphincter. The water and food particles are strained through their four gill baskets, with water slowly being pressed back out of the sphincter. These organisms have high food and oxygen requirements to fuel the stresses of repeated powerful movement. As such, the jelly lungs are the first of Lapis's life forms to evolve gills. It may seem that stone xanthofols have taken the spotlight. However, another closely related line of macaronophytes has quietly made an even greater leap. This is a Flake Xonthofol. It doesn't appear particularly remarkable, although its holdfast now grows in a layered, flaking manner. It's very small, forming a lichen-like rubbery crust over rocks and gravel. The Flake Xanthofol isn't remarkable due to its form, but rather due to its genetics. They're able to alter the process of mitosis into meiosis, producing 4 unique haploid cells from a single diploid cell, instead of 2 identical diploid cells. In other words, they produce gametes, which can fuse. These are the first xanthofols on Lapis to undergo sexual reproduction. Like the motilomorphs before them, sexual reproduction brings heightened genetic diversity, and with it, disease resistance and unparalleled adaptability. The future of Xanthofolifera, and the face of Lapis itself, lies within this humble flake. Certain patterns, such as the glide reflection and other fractals found in Earth's organisms, are incredibly simple and likely structures to find throughout the cosmos. Life on Lapis seems to echo Earth's ancient past quite closely, but it would have been impossible to predict a bird from Earth's Ediacaran biota. Lapis's ensuing endemic grandeur is equally obscured by the steady hand of time. Thank you for watching. This project takes a lot of time, research, and thought, and stuff. I'd love to hear what you think of the direction so far in the comments down below. Despite what episode 1 suggests, I no longer have a Patreon, but I still do have Instagram, and have yet to use Twitter more than once, so here's Instagram. Citations for images I used are in the description, as well as some further reading considering some of the topics I discussed in this video. The next video will be about the first mass extinction of macroorganisms on Lapis, the substrate turnover brought about by the Worm Age.